Hello, morning. So, we're going to continue with integration by substitution, and then later we are going to do integration by parts as well, and that should cover everything you have to know for. Oh, wait, there's also one more. Integration of 1 over 1 plus x squared. So we do those two things, and that should cover everything you have to know about this chapter. So all that's left is for you to do the past years. Okay, let's get started. Put that here. Right. Before that, let me just show you guys how to integrate definite integrals, those with limits, if you're using integration by substitution. So let me just pick a quick example here. Let's say we go with this one. This is from your textbook. So let's say you have 1 to 5 x squared and then x cubed plus 1 square dx. Okay. So if you look at this, you see that this guy is fx and this guy is kf prime x, which means this fits the whole integration by substitution form that we need. So we're going to start by saying u is equals to x cubed plus 1, and du dx is going to give us 3x squared, which means dx must be equals to du over 3x squared, right? So we're going to take that, I'm going to chuck that in here, and then we're going to get x squared here, and then u squared, and then du over 3x squared. And you can see the x squared, so it cancels with this one. Now, a common mistake that people tend to make is they would retain the same limits. They would put 1 and 5 here. But the thing is, these limits are only for when it's x. Now you've changed the u, you have to change it to u as well. So what you have to do is, I can say that since from this guy here, if x is equals to 1, u must be equals to 1 cubed plus 1, which is 2. If x is equals to 5, u is equals to 5 cubed plus 1, which is equals to 126. So you're supposed to do this, and then you put in your new limits, like so. Okay. And then you integrate this normally. You're going to factorize out the constant here, and then this is going to give me u cubed over 3, and then 2 to 126. Like so. Alternatively, what you can do is you can change this back to x, which means you would get x cubed plus 1 over 3, which means your limits, you have to change it back to the old limits, so you get 1 to 5. But in both cases, you would get the same answer. So since you've already changed the limits, it's easier to just do this, which means you're going to get 126 cubed. Wait, no. I think I've messed up something. Hang on. U cubed over 3. U is x is 5, so 5 cubed is 125 plus 1, 126. Did I mess something up? Where's my calculator? U is x cubed plus 1. Okay. 126 cubed is some gigantic number, so I feel like we get something weird though. Hang on, let me just check. Minus 8 over 3 divided by 3. So you get 200,000. Huh. 126 divided by 3. I should get 14. That's strange. Oh. Oh, okay. I forgot to put a cube here. Okay, no wonder. All right, so you should end up with the same answer. Yeah, there we go. So this would give you 1 over 3, and then 126 cubed over 3 minus 2 cubed over 3, which is roughly 20,000 something. And if you work this out, you get the same value. So there you go. What? You got 14? Let me check the answer. This is 8b. Where's my answer here? 8b question. No, it should be 200 something. 200 something thousand. Not 14. If you get 14, that means you forgot to cube it over here. I also forgot to do that earlier. Yeah, you should cube this guy. Yep, anyway, so there you go. Yeah, so before you evaluate the integral, make sure you're using the correct limits. Okay, so right, there's actually another kind of integration by substitution that I haven't shown you. So let me just show you that. So this happens when you have you're integrating gx and then bracket fx to the power of n dx, where gx, hang on, such that gx and fx are linear, and n is not -1. Well, actually, n can be -1. It doesn't really matter. You can still integrate by substitution. Okay, so whenever you see something like this, you can actually integrate by substitution as well. So let me show you an example. Let's say you're trying to integrate x and then square root of x minus 9 dx. Okay, something like this. You can see that the n in this case is going to be a half because it's a square root, but then fx and gx are both linear functions. So what you want to do here is you want to say let u be equals to x minus 9, which means x must be equals to u plus 9. Okay, so we can actually rewrite this integral here as u plus 9 and then square root of u, which means du dx is going to be 1. So du equals dx. So you can just replace this with du. Okay, so the reason we are doing it like this is because now we can expand this and we're going to get u 3 over 2 plus 9 u half du. You can't do that previously for this one because this one actually involves an expansion using the general binomial formula, the binomial theorem, the one that we did a couple chapters ago. So if you expand this using the general binomial theorem, you would get an infinite number of terms. Okay, so instead of doing that, you should just substitute u into this function here, which allows you to get a finite number of terms. And then you can integrate the terms separately, and you're going to get u 5 over 2 over 5 over 2 plus 9 u 3 over 2 over 3 over 2. So you're going to get 2 over 5 here, u 5 over 2 plus 3 plus 2 over 3, 9 u 3 over 2 plus c. I forgot to put a plus c here. Okay, and then now you're going to replace the u with x minus 9. And done. There you go. Okay, so that's it. Okay, so oh, actually, let me show you another one as well. Let's say something like this. suppose you have integrate x plus 1 over the square root of 3 minus 2x dx. Okay, and you want to integrate this. So if you rewrite this, you're going to get x plus 1 and then 3 minus 2x to the power of negative 1 over 2. And if you see, this is actually two linear functions, kind of like this. Yeah. Oh, actually, hang on. Yeah, two linear functions like that. So you can actually just substitute u with the guy in the bracket. And you're going to try to make x a subject here. But before that, let me just differentiate this. You get negative 2, which means dx is equals to negative 1 over 2 du. All right. And then we're going to try to make x the subject, which is going to give us 3 minus u over 2. There we go. So that's going to give me 3 minus u over 2 plus 1. And then this guy is u to the power of negative a half. And then negative 1 over 2 du. Okay, so we're going to take 1 over 4 out. Sorry, oops, I messed up. Hang on. Let's simplify this guy first. So what do we get? We get 3 plus 2, which is 5. So 5 minus u over 2 times u negative a half times negative 1 over 2 du. Then we're going to factorize the negative 1 over 2, 1 over 4 out. So we're left with 5 minus u times u negative 1 over 2. And then we're going to expand this, which is going to give us 5u minus 1 over 2, and then minus u 1 over 2. Okay, and now we can integrate them separately, which is going to give us 5 u 1 over 2 over 1 over 2 minus u 3 over 2 over 3 over 2 plus c. And then finally, we're going to put in the substituted u here. So we're going to get 3 minus 2x to the power of a half. And then, okay, let me just simplify this. Go away. So we should get a 10 here. And then u. Oh, wait a minute. It should be, yeah, okay, no, it's fine. u 1 over 2. Yep. There we go. And this guy here is 2 over 3. 3 over 2 plus c. So that's going to give me negative 5 over 2. 3 minus 2x and then a half. And then plus 1 over 6. 3 minus 2x to the power of 3 over 2 plus c. And done. Okay. So if both of these are linear functions, you can do a double substitution. You substitute this and you substitute this, and then you do integration by substitution as you would normally. Okay, so that's done. Right, moving on. What does that have to do again? I have to show you integration by parts. But before that, let me show you the one that involves partial fractions. Okay, let's see. What can we do here? Okay, let's do this one. Integrate x minus 4 over 2x minus 1 x plus 1 squared dx. Okay, if you get something like this, you can see that this actually, there's two terms down here, two functions. This, you have to do partial fractions first. Okay, so if you can't do integration by substitution, the next thing you should check is whether you can do partial fractions. If you can, usually you have to do that first. So let's do partial fractions. This guy's going to give me a over 2x minus 1 plus b over, bx, no, hang on, plus b over x plus 1 squared plus c over x plus 1 dx, right? And let's try to work out what a, b, and c is. So we have a times x plus 1 squared plus b times x plus 1 times 2x plus 1 plus c times 2x minus 1. Oh, whoops, this should be minus 1. Equals to x minus 4. Okay, so let x be equals to minus 1, which means a and b disappears. So we have minus 3c equals to minus 5. Therefore, c must be 5 over 3. Okay, then if x is equals to 1 over 2, then b and c would disappear. So we have a is 3 over 2 squared, which is 9 over 4. So we have 1 over 2 minus 4 is negative 7 over 2, I think. So a must be equals to negative 14 over 9. Right? Yeah, I think so. Let me just check. Wait a minute. What? Seems like I've messed up. Hang on a second. If x is minus 1, this one and this one disappears, so we're left with minus 3, then this minus 5. Why do they get something so different? Hello? Did I write down? Oh, I see. The question should be x plus 4. Okay, fine. Which means we would get minus 3c equals to 3. Therefore, c is minus 1. Okay, that's much better. Instead of all these weird fractions. So x is a half, which means we get half plus 1 is 3 over 2, so a 9 over 4 equals to half plus a 4 is 9 over 4. Therefore, a is 1. Okay, and then we're going to say when x is equals to 0, what do we get? We have 1 times 1 is 1 plus b, and then we have 2 here. No, not 2. 1, and then negative 1 minus 1 minus 1, and then 4. So we have negative b. This is plus 1, so 2. Okay. Wait, b is minus 1. Negative 1. A is... Wait, a should be 2. What? Hang on. If x is a half, this disappears, and then we have half plus 1 is 3 over 2. 3 over 2 squared is 9 over 4. Okay. Then half plus 4 is... Oh, 9 over 2. Half plus 4 is 9 over 2. So a should be 2. Okay. Which means this guy should be a 2. This guy should be a 3. This should be a 1. There we go. Yeah, okay, that's correct. So, putting that in here, get 2 over 2x minus 1 minus 1 over x plus 1 squared minus 1 over x plus 1 dx. Okie dokie. Now we can integrate them separately. So the first one is going to give me 2 ln 2x minus 1, and then differentiate the 2x minus 1, we get 2. And then here we are going to get x plus 1. X plus 1 to the power of 1. Okay, you know what? Let me just try to write it like that. This is actually x plus 1 to the power of minus 2, right? So when you integrate this guy, you would get x plus 1 to the power of minus 1, and you divide by the derivative of the function, which is 1. Then this guy is going to give me ln modulus x plus 1 divided by the derivative, which is 1, and then plus c. So simplifying this, we get 2x minus 1 minus 1 over x plus 1 minus ln modulus x plus 1 plus c. And if you have 2 lns and you are subtracting them, you are actually dividing them. So you get 2x minus 1 over x plus 1 minus 1 over x plus 1 plus c. And there you go. Okay. Right then. Okay. So basically, do partial fractions first, and then you integrate. Nothing that special. You already know how to do partial fractions, so I shall leave you to do to handle the rest. Okay, so next up, we're going to do integration by parts. Okay, so let's move this over here. So for integration by parts, let's say they ask you to integrate x e to the power of x dx. All right, so you can see here that let's say this is the function fx. This guy has nothing to do with fx, because if you differentiate, so remember when you have an exponential function, right? If you have an exponential function, usually you replace the u with whatever function you have up here. So let me just replace this with something else. Let's say this is 2x plus 1, okay? So usually what you would do is you say u is equals to 2x plus 1, right? And then you try to integrate by substitution. But the problem is if you differentiate this guy, you would actually get 2, and then you're not really going to do much here. Even if you try to replace the x with u, let's say you make x a subject, you're going to get u minus 1 over 2, and then you replace all of this entirely with u, you know, something like this, and then maybe dx is equals to du over 2, so you get 1 over 2 du. You still can't really do much because the u's are in, how should I say this? The u's are in different orders, right? This one is down here, this one is up here as a power, so you can't actually continue. So what should you do? So if you try integration by substitution and it doesn't work, if you try partial fractions and that doesn't work as well, that means you have to try the last thing, which is integration by parts. But you always try substitution first if you can. If you can't, then you do partial fractions. If you can't do that, the last resort would be integration by parts. So how do we do integration by parts? Okay. So this actually starts with the product rule. I'll show you how you get the formula. Actually, you know what? I'll show you the formula first. So whenever you integrate u dv, you will get v minus, what was it again? Oh, sorry, I messed up. uv minus v du, like that. Okay, so the dv here is actually a short form for dv over dx. And there's actually a dx here as well. Hang on, you know what? Let me just rewrite this. So this actually means u dv dx, and there's a dx here, equals to uv minus v du dx, and there's a dx here. So this is what it actually looks like, but typically in the textbook they would sort of cancel these things, and then they would just give you this guy here. Okay, so where does that come from? This actually comes from the product rule. So the product rule tells us that if we differentiate u and v, where u and v are functions of x and are different functions of x respectively, so u is actually, you know, fx, and v is actually gx. But instead of writing fx and gx, because that's too much work, because we're just going to leave it as u and v. So when you differentiate u v using the product rule, you actually get u and then dv dx plus v du dx, right? Product rule. And then if we rearrange this, let's say we're gonna move this guy here, and then we get d dx uv minus v du dx. Okay, I'm just making the second term the subject here. And then what we can do is we can integrate both sides with respect to x. Okay, we integrate both sides with respect to x. And as you can see, this guy here, the integral and the derivative are inverse functions of one another. So going back to what we've done in AS, or maybe even AddMath, if you have a function and then you put it into the inverse function, you just get the original number x. You always just get x, okay? So that means the inverse function and the regular function, d dx, will just cancel each other out. So you would end up with uv minus v du dx dx. This guy is u dv dx dx. And as you can see, we can cancel out the dx's, and you end up with the formula for integration by parts. Okay, so how do we actually use this formula? Well, let me just show you. The first thing you're going to do is assign one of these things as u and one of these things as dv. So usually what you want to do is assign u to the thing that when you differentiate, it becomes simpler. Okay, so in this case, you want to say u is equals to x and dv is equals to e to the power of 2x plus 1. Because we have to work out what du and v is as well. So du is going to be 1 because when you differentiate x, you get a simpler term, which is why we assign x as u. Okay? We don't assign x as, you know, we don't assign u as this guy, because if you differentiate this, you're not going to get a simpler term. You still end up with some exponential function. So this guy, if you integrate this, you would get e 2x plus 1 over 2. Okay? Now that we have done this, we can actually use our formula and get what we want. So we have uv, so u times v, so that's going to be x times e 2x plus 1 over 2. Okay, and then minus the integral of v du. So v is this guy. du is 1, so times 1, and then dx. So remember to write the dx here, even though the formula here has omitted the dx, but it's omitted only because we have done this cancellation here. But technically what's happening is you have to still write the dx. You should always write dx at the end of the integral, otherwise it doesn't mean anything. And you might lose marks because of that. Okay, so that's going to give me x over 2 e 2x plus 1 minus 1 over 2, and then we integrate this guy again, which is going to give us again over 2 and then plus c. And that's how you integrate by parts. Okay? Right, let me show you another example, a slightly more complicated example. So we just move that down here. Example 6. So let's say I ask you to integrate x squared and then e 2x dx. Okay. Again, we're going to use the integration by parts formula. Let me just write it down here so you can refer to it. Integrate u dv equals to uv minus v du. Okay, so first let's assign something to be u. Always assign the x squared or x to the power of n to be u. So du equals to 2x, okay? And then dv is e to x, which means v must be 1 over 2 e to x. All right, so next up, we're gonna use the formula and plug that in. We're gonna get uv, which is x squared over 2 e to x, and then minus v du. V is a half e to x, and du is 2x, and then dx. Okay, simplifying this this guy, we get this minus a half, and then actually we can take the half and the 2, they cancel out, so they're gone. So we're left with x e to x dx. And now we have to do another integration by parts, because here we are kind of stuck again, right? So you have to do an integration by parts in an integration by parts. So we're going to do that again. I'm going to say u is equals to x. So du is 1. dv equals to e to x. And then v is equals to 1 over 2 e to x. And then we continue again. So uv is x e to x over 2 minus v du. V is half e to x, du is 1, and there we go. Okay, and then now we try to simplify this, and this is plus a half, so 1 over 4 e to x plus c, and done. There you go. So for this kind of question, you have to do double integration by parts. Okay? What if you have integrate x cubed e to x? Then you have to do triple integration by parts. So hopefully you can see the pattern here. I'm not going to do that because it's super tedious. Okay. All right, so moving on. What if you have, let's say, x sine x? So again, this involves integration by parts. So let me just show you this very quickly. U is equals to x, so du is 1, dv is sine x, v is cos x. Okay, so putting in our formula, we get uv, which is x cos x minus v du. So we can end up with x cos x. Integrate cos, we get sine plus c. And done. There we go. Easy peasy, right? Okay. Next up, let me show you what happens if you have something without an x in there. So let's say you have Integrate sine x cos x dx. So there's actually two ways of doing this. So the first way of doing this involves using the identity. So remember, one of our identities is what was it? Sine 2x equals to 2 sine x cos x, right? So sine x cos x must be a half sine 2x. So you can simply use this identity and get whatever you want to get, which is the recommended method. So if you remember your identities, it's usually best to use them because it simplifies the workings a lot. So in this case, you would get, what happens if you integrate sine? You get cos, right? Negative cos. And you divide by the derivative. And done. Okay. Now, what if you were to integrate by parts? Technically, you can, though I wouldn't recommend it. In this case, you can assign one of them to be u. Using the formula, we get, let's see, what do you get? You get uv minus v du. Oh, whoops, I messed up. Oh, go away. Now, if you look closely, you will see that this guy is exactly the same as this guy, right? So we're gonna call this guy an unknown. So we have I is equals to sine squared x minus I, which means 2i must be equals to sine squared x, which means I must be equals to 1 over 2 sine squared x. There's a plus c here that I forgot. So there you go. But then you might be saying, wait a minute, this is not the same as this. So how can it be that it's correct? Well, using our identity for the double angle for cos, you remember there's one where it says it's 1 minus 2 sine squared x, right? Which means sine squared x is actually 1 minus cos 2x over 2. So using this identity, I'm going to put that in here. We are going to get 1 minus cos 2x over 2 plus c, which is 1 over 4 minus 1 over 4 cos 2x plus c. Right? Hang on, let me just check. Yep. So you can see that this guy, there's a negative in front, same as this guy here, and then 1 over 4 plus c is just another constant. So let me just write that here. Hello, hang on. Negative 1 over 4 cos 2x, and then plus 1 over 4 plus c. So this 1 over 4 plus c is just another constant. We'll call it c prime. So you can see these two are actually equivalent. So you can do integration by parts, or you can use the identity. Again, I recommend using the identity because it's faster. Okay, let's do one more example. Let's say you want to integrate e to the power of x and then sine x. Okay, and you can't use integration by substitution. You can't do partial fractions, which means you have to do integration by parts. So let's say u is ex. That means du is also ex. and then dv is sine x, which means v is negative cos x. Okay, using our formula, we get uv, so negative ex cos x minus v du. Simplifying this a little, we get this. And we can't really do much, so we are just going to have to do another integration by parts again, because we can't evaluate this, and this is not the same as this. So we're going to do integration by parts again. All right, so we're going to say u is equals to ex, du is ex, dv is cos x, that means v must be sin x. Okie dokie, let's continue. uv, we get ex sin x here, minus v du, which is ex sin x. Okay, and remember this guy is actually integrate ex sin x here. Okay. Now, if you look closely, you'll see that this guy is the same as the original function. So we're going to call this guy I. So we're going to have 2i, because I'm going to move this thing to the left, equals to negative ex cos x plus ex sin x. Therefore, I must be equals to 1 over 2 ex sin x minus ex cos x, which is actually 1 over 2, and then there's ex up here, sin x minus cos x. And that's how you integrate this guy, because this guy is I. Okay, so this is kind of like an infinite integration by parts, because if you keep going, you can go on forever, because this is an alternating kind of function. So you need to recognize that this guy is actually the same as this guy, and then you move this guy out here, and then you move it back. Okay, so one last example. One more example. Integrate ln x. So you know you can differentiate ln x, but you can't actually integrate ln x. Or can you? You can. The way you integrate ln x is by using integration by parts. And the way you do that, wait, you might be saying, hang on a second. There's only one function, ln x. But I thought when you integrate by parts, you need two functions, right? So how can I integrate if there's only one function? You can always insert a dummy function. And you do that by putting a 1 times ln x here. So the 1 is your dummy function. So we're going to say u is equals to ln x, du is equals to 1 over x, dv is 1, and v is x. Oh, and now we integrate by parts. So uv is x ln x, minus v du is x, v du, wait, no, x, so uv minus v du, okay, x times 1 of x. Ta-da! This is how you integrate ln x. Okay? And we're done. Oh, we are not done. It's one more thing I haven't shown you. Should I show it to you now, though? Yeah, might as well, since we are almost done. Okay. All right, so what if you were to integrate 1 over 1 plus x squared? What do you think you would get? Hey, Elise. Morning. Hello. Well, if you remember what we did back in differentiation, if you were to differentiate arctangent x, you would actually get 1 over 1 plus x squared, right? You remember this? So if you integrate 1 over 1 plus x squared, you should get arctangent. So this would give you arctangent x plus c. Not very surprising there, I think. Now, oh, whoops, hang on. Go away. What if I were to do integrate 1 over 1 plus a function of x squared plus c, dx, sorry. Well, this guy is actually going to give me 1 over f prime x, and then arctangent fx plus c. There. So generally, this is the kind of thing you would expect to get. This one is using the substitution. So you can try proving this on your own, but all you have to do is use integration by substitution. All right, let's do some examples. Let's say we have integrate 1 over 1 plus 16x squared. Okay, so this one you can actually rewrite this as 1 over 1 plus bracket 4x squared. And as you can see, this is actually this form, which means you would get 1 over 4 arctangent 4x plus c. There. Done. Okay. Another example. What if I were to ask you to integrate 3 over 4 plus x squared dx? So what you got to do here is you need to make this look like this, okay? And you can do that by factorizing out a 4 at the bottom. Then we're going to take out the 3 over 4 here. And then you can see that this is now like this. Ta-da! So now we can just integrate normally. We're going to get... So what happens when you differentiate x over 2? You get 1 over 2, right? So you get 1 over 1 over 2. And then you get arctangent x over 2 plus c, which means you end up with 3 over 2 arctangent x over 2 plus c. And done. Okay. That's it. We are done. Da-da-da-da. Okay, so we are done with integration. Everything. Let me just check, see if there's anything else we are missing. we are finished. Ho ho. So now you should be able to do the rest of 8c. Try the rest of 8c. No, was it 8c? Hang on, let me check. I think it was 8d. Yeah, the rest of 8d. So try the rest of 8d. And then you can also do 8e, 8f, 8g, and 8h. Oh, there's actually one more thing I forgot to mention. One more important thing I forgot to mention. Yes, let's do one more example. One more example. Let's say we integrate 0 to 1 x e 2x dx. So what happens if you have a definite integral and you have to use integration by parts? All right, let's do this real quick. U is x, du is 1, dv is e to x, v is 1 over 2 e to x, right? So using our formula shenanigans thingy, we get x over 2 e to x minus v du okay, so what happens to your limits? Your limits, I would recommend you do it like this. You put 0, 1 out here. Okay, don't put it inside the integral. So you do the limits at the end. So let's try to simplify this guy first. So we're going to get 1 over 4 e to x. And then now you put in the limits. So you get 1 over 2 e2 minus 1 over 4 e2 minus, this one is 0. This one is minus 1 over 4 e0. So you end up with a half minus a quarter is a quarter plus 1 over 4. Okay, this is what I recommend doing. You deal with the limits at the end. Okay, that's it. We are done with integration. So you should be able to do everything that I've given you, including all the exercises and the past years. So I highly recommend doing these because this chapter is immensely important. And if you look at the past years and how thick it is, you'll see that it is very popular in the exam as well. So I would say it's close to 30% to 40% of the entire exam paper. So please do these questions. I can't stress how important this chapter is. Okay, we are done. All right. So since I haven't received any questions from you guys. Nope, nothing. So we shall stop here for today, and I will let you carry on with the questions over the weekend. Oh, thanks for the follow, Ellie Catterley. Yeah, I shall see you guys next week. So next week will be my last week with you guys. So next Thursday will be our last class before you go for your term break until September, I think, because August is your term break, and then half of July is your term break. And Mr. Zikri will take over the class in September. Yeah, so bye-bye. Hmm.